Hello, this video is made as a recap of our Wednesday Zoom lesson on September 30th, week 5 for Physics A. This lesson had some unexpected twists and turns because we were having massive audio problems with this computer, and hopefully the school will figure out what's going on. It might have a bad microphone. So I apologize for that, and hopefully this video will kind of help make things up. The big thing I really wanted to do today was give a pep talk. I think you guys are doing a really good job. I know there's just tons of information coming at you, and ordinarily we'd be talking about this a lot in class and making sure we're all on the same page about these problems. So please be in touch. Please ask questions. I promise we can get all you where you need to be. The other thing we really did today is we looked at a test review for next week's test. And let's take a look at that test review. So overall, the test review is kind of a mix between two types of problems. There's some graphing, and then there's some word problems. And let's just go through the whole thing in here so that you can sort of feel like you know what's going on. On these graphing problems, sometimes it looks like the motion rapidly changes partway through the problem. And it almost makes sense to put a dotted line through the place where the motion changes, just to signify that you're really looking at two different problems, before the change and after the change. So if you do that, we could start with the velocity graph on this first one, and we see that we have a constant velocity. So if we're going up to position from velocity, a constant velocity means our position keeps getting bigger and bigger, but at a steady rate. In other words, a linear position time graph. So up to the dotted line, I have a line. Then my velocity starts to change. Notice it starts decreasing. I'm still going forward in every case, so my position's still going to get bigger and bigger, but less and less so, until eventually I stop moving. Zero slope on a position time graph, zero velocity. So that part I hope is not too scary. To go to acceleration, you just look at the slope of the different velocities. This velocity is constant. That means I'm not accelerating, so I have an acceleration of 0. This velocity is negative, and it's decreasing at a steady rate. That's a constant negative acceleration. On the second one, my position time graph first is parabolic. In other words, I'm getting faster and faster and faster. So that means a velocity that's steadily increasing. After a while, my position continues to get bigger, but at a constant rate. So that's a constant velocity. On the acceleration graph, I have a positive acceleration. My velocity is getting bigger at a steady rate. And then my velocity stays constant. So I have no acceleration. On number 3, there were really two possible answers. All the acceleration graph tells you is that you have a constant negative velocity. And that means you have a constant negative acceleration. And that means your velocity graph is going to have a negative slope. But it could be this one or this one. And there's no way to tell without being told an initial velocity. So either of these would be fine. And when you do your position graph for the two of them, they could be very different. In this case, where I start off with positive velocities, that means I'm going to have positive slopes at the beginning and negative slopes at the end. So I'll have an object that's turning. If I always had negative velocities and it's just got more and more negative, then I'll just have a position graph that shows speeding up in the downward direction. So practice those, work through those. There was the other worksheet we worked on this week, or we'll work on it for cohort B tomorrow. So I think that'll give you a little more practice with these. The rest of this is word problems. So let's just look at them real quick. In this first problem, it gives us an initial velocity of 7 meters per second, and it tells us they go 1.35 meters. So the givens here are 7 meters per second and 1.35 meters. But notice I've made two other assumptions. I've assumed that if they're sliding into a base, they're hopefully going to stop, or else they're going to get tagged out. So I put my final velocity at 0. And XO is always 0 unless you have a reason to choose otherwise. So with that information, I was able to solve for acceleration. And then having acceleration, I could use the same data to plug into the easier equation and get a time. I feel like these problems are the ones stressing students out the most, and a lot of the questions people are asking have to do with the assumptions. So don't forget, you've got a number of things you can assume, and they are listed in the Flickr album. Let me show you where. They're back kind of before the Angry Bird lab. And before the worksheet we did last week. Those answers are all here. They're on this one that has the popcorn and the hot sauce covering up something on the board. So these are the things you can assume in these problems. And just read through these and practice these, and hopefully that will help you on the positive physics as well. Okay, back to our test review. These type of problems, here's another one. I think this is another really good one where you have to be careful with your assumptions. It only tells us that the baseball is going to be in the air. It doesn't tell us how long it's going to be in the air. It just tells us we launch it with a speed of 4 meters per second. So everything else has to be kind of teased out by us. So there's my 4 meters per second. But I know if I throw a ball straight up, eventually it's going to get to the peak of its flight, and it's going to have a velocity of 0. I also know that gravity is going to be the force that's accelerating it. So an acceleration of minus 9.8. And again, XO is always 0 unless you're told otherwise. So that gives me enough to use the first equation to solve for time. And since that's the time it would take to go up, 0.408 seconds, it's going to take that much to go back down too. So my overall answer is 0.816 seconds. As far as how high will it get, now I can use my time that I just got, and I could plug into my position time equation, and I can get a height. So hopefully that helps there. Last thing we're doing is really the definitions of distance, displacement, speed, and velocity. And basically distance and speed are agnostic about direction, whereas displacement and velocity care. So we're calling the westbound trip to New York City, we're calling that the negative direction, and the eastbound trip to Niantic the positive direction. And in each case, New York and Niantic are 115 miles apart. That's their distance. But they have a different displacement on these two trips because displacement cares about direction. So going west is negative 115. Notice the distance for a round trip is 230. You take the absolute value of each displacement and add them up. So if you were going to go from Crescent Beach to New York City and back to Crescent Beach, that would be 230 miles. But displacement only cares about your overall change. So your westward displacement would be canceled out by your eastward displacement. And at the end of the day, you're back in the same place. And then that plays out with speed and velocity too. If you are calculating speed, you do distance over time. If you're calculating velocity, you're doing displacement over time. So your average velocity on a round trip is 0 because you end up back where you started. So anyway, I know that stuff you guys can do. Be in touch if you need help. I'm sorry about the tech issues today, and I'll see you soon.